so according to my notes, we finished Friday, right, with example 1F there, right? You did these two problems in your notes, is that correct?
Yes.
All right, so if you flip over to the next page, right, there are there's one more logarithmic equation that we have to solve, and 3 more exponential equations. And so it's sort of like more of the same of what we've been doing. So those 4 solutions are on video. And the link to that video is posted on Oaks. Okay? I think it's like an 8-minute video going through, right? I can clip through these pretty quickly because I write on the board right before I do the recording. And so I can just walk you through the solution on the board. Okay? All right. So then if you flip over to the next page, we're going to find the inverse function of a couple of functions. And we studied inverse functions, I believe, back in chapter 2, section 2.8, if I recall correctly, where we learned about inverse functions. So in example 2a, we have f of x is equal to e raised to the 3x minus 1 power plus 5. And we got to find the inverse of that one-to-one function. Well, before we do, I want to make an observation about this function right here, okay? About its domain of this function. And back in section 5.1, right, we learned about the natural exponential function, f of x equals e to the x. Here's the graph of the natural exponential function, f of x equals e to the x, right? Goes up from left to right. And we noted on the previous page that the domain, right, in general, the domain of any exponential function, a to the x, and that includes e to the x, its domain is all real numbers, minus infinity to plus infinity. So, the graph of this function is the graph of the natural exponential function, okay? But it's the graph of this function is the transformation of the graph of the natural exponential function, f of x equals e to the x, right? And so, none of the transformations that are performed on this function, okay, affect the domain. So the domain of this function is also minus infinity to infinity, just like it is for e to the x, okay? That's my point, okay? None of the transformations on f of x equals e to the x affects the domain, okay? So now let's find the inverse function for this function, okay? And if you recall, there were 4 steps in finding the inverse function. Do you remember what step number 1 was? Right? This is the kind of thing you got to, you have to pull together for the final exam, right? Because you'll have to find an inverse function of something on the final exam, right? Step number 1 was replace f of x with y. Do you remember what step number 2 is? Say what? Replace x with y and y with x, right? You got to switch x and y. So replace y with x and x with y. And now we solve for y. And so the first thing you would do in solving for y, right, is move the plus 5 to the left-hand side by subtraction. So we have x minus 5 is equal to e raised to the 3y minus 1 power. And now y is in the exponent on the number e. And so to isolate y on the right-hand side, we're going to get rid of the e, right? How do we get rid of the e again? Natural log, right? So we can take the natural log of both sides. We have the natural log. Now you're taking the natural log of the entire left-hand side. So x minus 5 has to go in parentheses, right? That's the argument in the natural log function. And then on the right-hand side, we have the natural log of e raised to 3y minus 1 power. So we have the natural log of x minus 5, and the right-hand side simplifies to 3y minus 1. Now, right, it's straightforward in solving for y. We're going to add 1 to both sides. We have 1 plus the natural log of x minus 5 is equal to 3y. And now we divide both sides by 3 to isolate y on the right-hand side. And when we switch the two sides, we have y is equal to 1 plus the natural log of x minus 5 over 3. So the instructions are to find the equation for the inverse. Right, so y equals this on the right is the equation. But typically you're asked, right, put the answer in inverse function notation, right? They ask for the inverse function. And so in inverse function notation, right, we replace y with f inverse of x. We have 1 plus the natural log of x minus 5 over 3. Okay? Are you with me on that? Okay. Now, here's the more difficult part. Use interval notation to state the domain and range of the inverse function. Okay. Well, we know how to find the domain. The only place in the inverse function where x occurs is in the argument going into this natural log function here, right? So to find the domain, right, for this function, we just set the argument x minus 5 greater than 0. Because you know you can't take the log of a negative number, you can't take the log of 0, right? You only take the log of a positive number. So we just set the argument going into this natural log greater than 0. So the domain set the argument x minus 5 greater than 0. Then we solve for x, add 5 to both sides, get x is greater than 5. And so in interval notation, the domain is parentheses 5 comma infinity. Now the range Now there's two ways to argue the range. Right? The range of this inverse function is going to be determined by the range of the natural log function. But it's also, we also know that the range of an inverse function is equal to, I forgot to write the domain up here, right? Should say minus infinity to infinity. But the range of an inverse function is equal to what? The domain of the one-to-one function, right? Well, we know what the domain of f of x is. It's all real numbers. And so the range, likewise, is all real numbers. And you could argue, looking at the inverse function, that that makes sense because the range of the natural log function is minus infinity to plus infinity. Okay. And so either looking at the natural log of x minus 5 and arguing its range is minus infinity to infinity, or looking at the domain of f of x, which is minus infinity to infinity, you get the range. Okay. All right. Any questions on that? All right, so let's take a look at B. Now we're kind of going the other way, right? In A, the one-to-one function was the transformation of the natural exponential function. In B, the one-to-one function is the transformation of the natural log function. So we have, right, the argument going into the natural log function is x plus 3. So we have the natural log of x plus 3, and then that minus the number 1. Okay. So the domain, the only place where an x occurs is in the argument of the natural log function. And so to find the domain of this function, we just set the argument greater than 0. So we have x plus 3 is greater than 0, or x greater than minus 3. And so the domain goes from minus 3 to infinity in parentheses. We'll use that to get the range of the inverse function. All right. Find an equation for the inverse function f inverse of x. So same 4 steps every time in finding an inverse function. Replace f of x with y. Switch x and y. Solve for y. So we got to isolate y on the right hand side. So we're going to move minus 1 to the right hand side via addition, right? Add 1 to both sides. We have x plus 1 is equal to the natural log of y plus 3. And now the only place where you see y is in the argument going into this natural log function. So we got to get rid of the ln. And so we make the left hand side and the right hand side exponents on the number e. Right? Left side, right side are equal, so I can make them exponents on the number e. Right? We got an exponential on the left, exponential on the right. Same base. Exponents must be equal, which they are. Okay? So we have e to the x plus 1 on the left, and property of the natural log function says this on the right is just equal to y plus 3. So now I subtract 3 from both sides and switch both sides at the same time, and I have y is equal to 3 plus e to the x plus 1. And instead of writing e to the x plus 1 plus 3, I like to put the 3 in front so there's no confusion where the 3 is going. It's not going up in the exponent, right? This is 3 being added to e to the x plus 1.
Do you have to subtract 3?
Yeah, you gotta subtract 3, sorry. So in this step, we subtract 3. So this is the equation for the inverse function. And then we replace y with inverse function notation. And we say we have the inverse function. Okay? All right. Well, look at the inverse function. The graph of the inverse function is just a transformation on the graph of e to the x, isn't it? So when you replace the x and e to the x with x plus 1, it just shifts the graph of e to the x plus 1, what, to the left 1 unit? And then when you subtract 3, it shifts the graph down 3 units. And so that has no effect on the domain, okay? So this function is still defined for all real numbers. So the domain is all real numbers. The range is equal to the domain of the 1-to-1 function. What's the domain of the 1-to-1 function? Minus 3 to infinity. And we're done, okay? So remember, the range applies to the y values, right? So the y coordinates in the graph of this inverse function are all greater than -3. Okay. Any questions on this? So this homework is due Wednesday night. Said it's been released, okay? And the video solution to 4 of those problems. Right, the link is on Oaks. All right, last section from chapter 5 is on application. So we're going to be focusing on exponential models in 5.4. Kelly, if you'll hand you.
Oh, I don't.
Oh, you don't
I
need one?
printed it out.
You what?
I printed it out.
Okay. Go ahead and. Yeah, you're getting your mail delivered to you. Yeah.
Thank you.
Yep. Yep. this deal. Give me a hand, Betsy. All right. So, at the top of page 1, right, it talks about exponential decay and exponential growth using this model right here, right, with the natural exponential function. So what I would like you to do is the very last page is blank. So before we do any examples, there are a couple of things I want to go over with you, so we don't have to keep deriving them in one example after another. So our math model for exponential growth and exponential decay is a of t equal to a sub 0 times e raised to the kt power. Okay? So t is the input variable, right? So t is time. And t is greater than or equal to 0. Okay? Time starts at t equals 0. And a sub 0 and k are constants. So if I evaluate this function at t equals 0, I have a of 0 is equal to a sub 0 times e to k times 0. K times 0 is 0, and e to the 0 is 1. So when I put in 0 in for t up here, the right-hand side just equals a sub 0. Okay? So the amount of the substance at time 0 is this constant a sub 0, and that's the initial amount of a substance or population. Okay. Not only is this model used to model the amount of a substance over time, but it also gets used to model populations, or populations of fish and things like that. Okay. K, this constant k, and the exponent on the number e has two interpretations depending upon the situation. Okay? It's called the growth rate. If it's greater than 0, which means the population or substance is increasing over time. And it's called the decay rate if k is less than 0. Okay? If k is positive, greater than 0, then the amount over time increases. If k is less than 0, the amount over time decreases. Okay? So that's why it's called the growth rate if it's positive, and the decay rate if it's negative. Okay? All right, so there's a couple of formulas that we'll find handy, so we don't have to calculate them every time. One is the time for a population to double in size. So we're talking about for the population to go from it's the initial amount, a sub 0, to twice its initial amount. Okay, that's what we mean by doubling. Right? So, capital T is the time it takes for the population to double in size, right? To go to 2 times its initial amount. Well, that has to, the amount at time capital T has to equal 2 times the initial amount. And in our formula over here, when I place little t with big T, I get a sub 0 times e to the k times big T power. These two on the right here have to be equal because they represent the same thing. So we set 2a0, a sub 0 equal to a sub 0 times e raised to the k times capital T power. And we're going to solve for t. Solve for big T. Well, you can see a sub 0 is a common factor on both sides. So we divide both sides by a sub 0. The a sub 0's cancel. And we're left with 2 is equal to e raised to the k times capital T power. So again, we're solving for big T. It's an exponent in the number e. So to get rid of e, we got to take the natural log of both sides. We have the natural log of 2 is equal to the natural log of e raised to the k times big capital T power. And so on the right-hand side, that just simplifies to k times t, k times big T. And now I divide both sides by k and switch to 2 sides. I get the time it takes for a population or substance to double is equal to the natural log of 2 divided by k. That's the formula. Okay. So given the growth rate, you can immediately calculate how long it takes for a population or substance to double. Okay? Any questions on that? That's a handy form, so we're not, for every problem that asks for how long it takes for something to double in size, we're not grinding through these calculations over and over and over again. Okay? Well, next, we're interested in not in the time it takes for a population to double in size, but for substance to decay in half. From its initial amount, right, to 1/2 this initial amount, right? When we say time for substance to decay in half, we're talking about from the time it goes from its initial amount to 1/2 its initial amount. So again, capital T is the time for the substance to decay to 1/2 of its initial amount. So A capital T is equal to 1/2 a sub 0. And on the right hand side of our model, that's also equal to a sub 0 times e raised to the capital a sub 0 times e raised to the k times big T power. So on the right hand side, these two guys got to be equal. So we have 1/2 times a sub 0 is equal to a sub 0 times e raised to the capital, raised to K times big T power. Well, again, a sub 0 is a common factor on both sides. So we divide both sides by a sub 0. And we're left with 1/2 on the left. Is equal to E raised to the K times capital T power. And so a formula for the time it takes for something to decay in half is going to be similar to the formula for the time it takes for it to double in size. So we take the natural log of both sides, and we end up with the natural log of 1/2 is equal to K times T, capital T. And when I divide both sides by K, I end up with capital T is equal to the natural log of 1/2 over K, where K is now the decay rate. Okay. K is negative. Okay. So 1/2, you know, is the same as 0.5. So you can write this formula as the natural log of 0.5 divided by K. And using the quotient rule, this is equal to the natural log of 1 minus the natural log of 2, and the natural log of 1 is 0. So you can also write this formula as minus the natural log of 2 over K. When you write it this way, this third step, the only difference between the time to double and the time to be cut in half is you put a minus sign from the natural log of 2. Okay. I don't care which of the three you use. All right, any questions on this introduction? If you have your scientific calculators, you might want to get them out so you can verify my calculations, because this is one of those sections where you have to have a calculator. So let's look at example 1. The number of certain species of fish can be modeled by the formula N of T equals, so in this case they replace A of T with N of T, is equal to 12 times E raised to 0.012 T power, where T is measured in years, right? So time is measured in years, and N of T is measured in millions. So we have little n of t is equal to 12 times e raised to 0.012 t power. Right, that tells us how many fish in millions there are as a function of time. So an A is, what is the relative rate of growth of the fish population? That is equal to the value of K. And K in this case is 0.012. And usually we like to express these answers as percentages. And so, to get the percentage, you just move the decimal place 2 notches to the right, and we have 1.2%. And because time is measured in years, right, it's 1.2% per year. What will the fish population be after 15 years? Well, to find what it would be after 15 years, we just put 15 in for t. So we have n of 15 is equal to 12 times e raised to 0.012 times 15 power, right? So now it's PEMDAS, right? Right, it's arithmetic at this stage. So you guys simplify the exponent. 0.012 times 15 is equal to 0.18. And now, you know, exponentiation comes before multiplication. So using your calculator, you should have like an EVX key on there. You do e raised to the 0.18. And when you're doing these calculations on your calculator, you don't have to write down the numbers, you know, to 50 decimal places. Right? You just leave the number in memory. And use all the decimal places until you get to your final answer. So e to the 0.18 is equal to 1.197 217.363. See, this is why you just use, right? I don't like writing these numbers down. Okay? I just leave the number in memory and then multiply by 12. Okay? And when I multiply these two numbers, I get 14.367. Now, why did I go to 3 decimal places? Because the population is in millions. So there's always going to be that question in your final answer: how many decimal places do you have to go? And you just have to use good judgment. Okay. So since our answer is in millions, I went to 3 decimal places, and so it's 14.367 million fish is what I got. Anybody get anything different? To 3 decimal places. Any questions on that? Okay. I don't think we can do problem 2 in 3 minutes, so we will stop here and pick it up here first thing on Monday. Yeah. You know, probably on this 4th exam, it'll come in 2 parts. You'll get the first part with no calculator, and then when you turn that in, you'll get the second part where you'll use your calculator. Yep. Have a good day, everybody.